Hey guys, we're going to have a quick video lesson about electric fields so that you can try out tonight's homework and see how it goes. So we've been working with this equation about electric force for a while now. The electric force equation's all right and stuff. We've been doing some work with it, and you know how to plug numbers into it. The good news is when you're calculating electric fields, all the things you learned how to do with electric forces are basically the same mathematically, right? So you're still talking about the same units, still going to be things like nanocoulombs, and the distance between, 2 points is measured in meters and stuff, and that's what R stands for. But there's some important differences that you need to understand conceptually. So one of these things is what electric fields are really supposed to tell you. So take, for example, a positive charge. Just hanging out here all by itself. That's a positive sign, not a T. Okay, so that positive charge is hanging out there. It doesn't have anything around it at the moment for it to push or pull on. You could kind of think of this as being sort of like the Earth before it had a bunch of satellites orbiting around it, right? The Earth, there it is, the Earth, had, no satellites except for, the moon way the heck off there somewhere. But it has around it a gravitational field, right? We learned that equation back when we did gravity. It was, the G equals gm over r squared equation. And we said, oh, gravitational field tells you acceleration due to gravity. The force equation, as you probably recall, looked very similar. Right, it had that extra little m in there. And so if you wanted to know the force that, a planet or something exerts on some object out there, you needed to know both masses and the distance between them. But to calculate the gravitational field, you just had to know how massive the planet was, so say Earth, and where exactly you were interested in finding the field. So if it was at the surface, we plugged in like the radius of the Earth. If it was higher up, where we might put a satellite, then we would plug in that distance there. And so with field forces, we always think about the field as causing the force. So there's another way that you can write the equation for the force of gravity, and that is by recognizing that gm over r squared, that part right there, is g. So if all of that right there is g, the only other thing left in the equation is the m. And so the force of gravity is mg. You've been using that equation since nearly the beginning of the year, right? Anytime we drew any sort of a diagram with forces, like a block or something, we would say, oh, the force of gravity on it is mg, and we drew it going straight down. And for those, g was always 9.8. But the point isn't that, g is 9.8 or something. It's this idea that the force of gravity could more conveniently in this case be written as mg, where g is the gravitational field. And so when we get to, when we're talking about electric fields in sort of the same vein, it's very frequently going to be the case that it's more useful to calculate the field at this point or that point or something like that around this charge than it is to calculate a force. Because, like we said, the Earth didn't always have a whole bunch of satellites around it. It may not, back, 200 years ago, there really wasn't a lot up there and close to the Earth for it to exert a force on, so to speak. But you could still say that it had a gravitational field at whatever height above it. And then if you put something in that field, then there would be the force on it. Okay, by the same token, if I were to calculate the electric field near a positive charge at, say, that point right there, and I knew that the electric field was some number, I could find the force on it by doing the same sort of thing that I did down with the gravity stuff down there, by saying, well, kq over r squared is the formula for electric field. And so that means the force on a charge in an electric field follows the equation QE. And it turns out that that is a much more convenient equation to use a lot of the time. Because, there may not always be two charges or three charges or something like that. And so it's often more useful to calculate the field and then say, all right, what's the force if we put some magnitude charge in it? Now, the next thing that we've got to talk about is, besides calculating electric fields, determining the direction of an electric field. So this is a relatively straightforward thing. Positive charges make electric fields that go out, away from them. So if I said, hey, find the electric field over here, a meter off to the right of this 2 nanocoulomb charge. And it's a positive charge. Positive charges make fields that go away from them. So the field at that point would point to the right. Okay, and if I wanted to know what that magnitude is, what's the number, how big is the field, we'd use our equation kq over r squared. All right, k is 9 times 10 to the 9th. Q, I said here, was 2 nanocoulombs, which you ought to know is to the negative 9th. All right, and if that distance there was, I don't know, let's say it's not 1 meter because that's too simple. Let's say it's 1 centimeter. Oh no. All right, well, if it's 1 centimeter, put it in regular meters. And then, of course, we square it. And so the answer we're going to get will be 18, 1, 2, 3, 4. Okay. So 180,000, 180,000 what? All right, the units for an electric field are, in fact, newtons per coulomb. Where that's coming from is the equation that I wrote down a minute ago, F equals QE. If you solve that equation for E, then it's F over Q. Okay, and force is measured in newtons, and Q's charge, that's measured in coulombs. All right, now, if you wanted to know something like, what's the force that field would exert on some other charge that was placed there, that's a question that we'll get to in a little bit, but it would just be that equation. What I want to look at next is, yes, but what if this had been a negative 2 nanocoulomb charge? How would things have been different? Well, okay. If that were a negative 2 nanocoulomb charge, only one thing would change. And that is that at this point, where I was looking at the electric field, I wrote a plus again. Silly me. Let's get rid of that. It's a negative. I meant to say negative. Okay, so that negative charge is going to make a field that points, instead of to the right, like we did with the positive charge, it would point towards the negative. So pluses make fields that go away. Negatives make electric fields that go towards, meaning towards them. Okay, so in my picture here, the 2 nanocoulomb charge would make a field at that point of exactly the same number. It'd be 180,000 newtons per coulomb, if I don't change any of my values. But The one for the positive charge would say is to the right, and the one for the negative charge we would have to say is to the left. Mr. Errico, are you saying that positives make fields to the right and negatives make fields to the left? No, I am not saying that. That would be extremely silly. It depends where you're looking at, okay? The real answer is pluses make fields that go away from them, wherever away from is in your diagram, and negatives make charges that go towards them, again, wherever that may be in your diagram. So if we have the plus up here, again, its own little space, it would make a field to the right of itself that would go to the right, because if you're off to the right of the positive charge, to the right would be further away from it. If we were asking about off to the left of it, the positive charge would make a field that would go also away from it, but in this case, away from is the left. All right, a negative charge would make a field that would go to the left if you're looking at a spot to the right of it, and to the right if you're looking at a spot that's off to the left side. Okay, so visually what you should be seeing here is pluses make fields that go away, negatives make make fields that go towards them. All right, now why is that exactly? What are we supposed to get from that, and why do we draw them that way? Well, it's because of this idea that we started with, which is that it's the electric field that exerts the force. So you shouldn't really think about the charges necessarily as pushing on each other. It's the field that one charge makes that exerts a force on a second charge that happens to come too close. All right, so if I put let's say a small positive charge right here. There it is, a small positive charge. Which way would that positive charge go? Meaning, which way would the big plus that I drew off to the left push it? Well, if you said, or thought, to the right, that would be the correct answer. It would, of course, go to the right, because like charges repel. If I put a minus there, it would go to the left. In terms of fields, then, what this means is that positive charges follow field lines, meaning it follows the electric field. That needs an S. Okay, so the plus charges will follow the electric field. Negative charges, on the other hand, go against the electric field. And so the plus would follow the field to the right, the negative would go against the field and therefore head to the left. So the reason we say that positives make fields that go away from them is because it shows the direction of the force that would act on a positive charge that you put close by. All right, if we go down and look at the negative here, we could see the exact same thing works by analogy. If I put a plus there, it would follow the field. If I put a minus here, it would go against the field. And that's what they would do. All right, I think we'll have to call that part 1 and head over to the next video, which is imaginatively going to be called part 2.